November 14, 1940. Coventry sleeps under a moonless sky. At 7:20 p.m., the first Hanklin 111 crosses the English coast. Its Nicobene radio beam guiding it straight toward the city center. Over the next 11 hours, 49 Luftwaffe bombers will drop 500 tons of explosives and 30,000 incendiaries. By dawn, the medieval cathedral is a skeleton of stone. 568 civilians lie dead, and 2/3 of the city's buildings are rubble or flame. Our Fighter Command manages exactly 0 confirmed interceptions that night. 0. This wasn't an exception. This was the pattern. Between September 1940 and May 1941, the Blitz killed over 43,000 British civilians and injured 139,000 more. Night after night, German bombers flew across the Channel, struck their targets, and returned home. While RAF Spitfires and Hurricanes, the celebrated heroes of the daytime Battle of Britain, sat uselessly on the ground. Those aircraft were built for daytime dogfights where a pilot's eyes were his primary weapon. But at 15,000 FT on a moonless night, human vision is worth nothing. A bomber could pass 200 yards away and remain completely invisible. The RAF tried everything. They positioned single-engine fighters in patrol boxes over known approach routes, hoping for lucky visual contact. Success rate less than 1%. They tried cat's eye patrols where pilots with supposedly superior night vision would lurk near searchlight batteries waiting for ground crews to illuminate a target. On a good night with a full moon and cooperative weather, a skilled pilot might spot a bomber silhouetted against clouds. Might. Flight Lieutenant Guy Gibson, who would later lead the Demusters raid, flew 99 night sorties in early 1941 and scored exactly 1 kill. The mathematics were brutally simple. A Henkel bomber measures roughly 57 FT across. At night, the average fighter pilot couldn't see it beyond 400 F a right. But to search a cubic mile of airspace flying at 250 mil a Reich, a pilot would need to cover 147 billion cubic feet, while the bomber was only occupying about 50,000 cubic feet of that volume at any given moment. It was like finding a specific needle in a haystack the size of Westminster, while blindfolded and sprinting. Ground controllers tried to help. They track incoming raids on their chain-home radar stations and radio vectors to airborne fighters. Banded at Angels 15 heading 270. The fighter would race to that position, but radar operators on the ground could only update positions every few minutes, and their accuracy wobbled by up to 2 miles. By the time a fighter arrived, the bomber had moved. The controller would issue a correction. The fighter would turn. The bomber would turn. The deadly game of blind Marco Polo would continue until either the fighter ran out of fuel or the bomber reached its target and escaped. Air Chief Marshal Hugh Dowing watched his nation burn. His fighters had saved Britain during the day, but darkness rendered them impotent. Industrial cities, Birmingham, Liverpool, Manchester, Glasgow, were being systematically destroyed. War production was being throttled. Civilian morale was cracking, and the Luftwaffe was losing fewer bombers per month to night fighters than to accidents during training. Something had to change. The RAF needed eyes that could see in the dark. They needed radar in the air. They needed it to work. And they needed it yesterday. Chain-home was magnificent and completely inadequate. By 1940, Britain's coastal radar chain was the most sophisticated early warning network on Earth. Those 350 FT steel towers could detect incoming bomber formations at 120 mph, giving Fighter Command precious minutes to scramble interceptors and organize defenses. The system had been vital during the daytime Battle of Britain, but detecting a bomber and killing it are entirely different problems. Here's what ground-controlled interception looked like in practice. A chain-home station picks up a raid crossing the coast. The operator reports it to Fighter Command. Hostile formation, 40-plus aircraft, Angels 12, Vector 285, speed 180 knots. A controller vectors the nearest night fighter toward the intercept. Steer 310. Climb to Angels 14. The pilot acknowledges and turns. 4 minutes pass. The ground radar updates. The bomber formation has turned slightly and climbed. New vector issued. The fighter adjusts. Another 3 minutes. Another update. The bombers have split into smaller groups. Now the mathematics get worse. Chain-home's radar accuracy was approximately 2 miles horizontally and 1,000 FT vertically. That's a search volume of roughly 13 million cubic feet. Inside that uncertainty bubble, multiple bombers might be maneuvering independently. The ground controller picks one radar blip and keeps vectoring the fighter toward it. "You should be very close now," he says. The pilot stares into darkness and sees nothing. He's probably within 2 miles of a bomber, maybe even the right bomber. But 2 miles of night sky is an infinite void. Some controllers developed an almost supernatural skill. Squadron leader John Cunningham's regular controller, Flying Officer Jimmy Ronsley, could read the cathode ray tube like a fortune teller reading tea leaves, anticipating bomber movements and placing Cunningham within visual range through pure intuition. But even Ronsley's success rate before mid-1941 hovered around 5%. 5%. For every successful interception, 19 bombers escaped. The problems compounded. Chain-Home was designed to look outward across the channel, not track aircraft already over Britain. Once bombers crossed inland, coverage became patchy. The home chain's radar beams were optimized for long range, not precise positioning, and the system was completely blind below $1,000 FTR. Luftwaffe bombers occasionally exploited this by dropping down after crossing the coast, disappearing from British radar entirely until they climbed to bombing altitude over their target. Ground clutter made things worse. Radar returns bounced off hills, buildings, and even weather formations, creating false contacts that controllers had to mentally filter out. On windy nights with heavy clouds, a single chain home station might show 200 phantom aircraft. Operators learned to distinguish real bombers from noise, but it was exhausting work that required intense concentration. Mistakes were inevitable. Then there was the human factor. A ground controller sat in a bunker, staring at a flickering green screen, trying to build a three-dimensional mental picture of a battle happening 15,000 FT above him and 50 mm away. The fighter pilot sat in a cramped cockpit, wrestling with instruments, throttle, and trim, while straining his eyes into darkness and listening to a crackling radio voice issue. Constant heading changes. Turn starboard 10 degrees steady. Target now 11 more, 3 miles slightly above. 3 miles still invisible. The pilot's neck aches from scanning. His eyes water from staring. His fuel gauge drops. And somewhere in the darkness, a Hankel crew is lining up their bomb sight on a factory. Britain needed the radar inside the fighter, behind the pilot's eyes painting the sky ahead. They needed the technology small enough to fit in an aircraft and powerful enough to give warning before a visual sighting. They needed something that seemed impossible in 1939. Edward Bowen didn't. Looked like someone about to change aerial warfare forever. The 27-year-old physicist worked at the secret Borsimana research station on the Suffolk coast where Britain's radar program was born. In 1936, Robert Watson Watt had proven radar could detect aircraft. By 1939, Bowen had been given an impossible assignment: shrink a radar station the size of a house into something that could fly. The prototype AI Machi AI stood for Airborne Interception was absurd by any reasonable standard. The transmitter unit weighed 220 lb. The receiver added another 180. The power supply and display unit brought the total to roughly 600 lb of equipment. For comparison, a Supermarine Spitfire's entire armament weighed 280 pounds. Bowen's team was asking pilots to carry more than twice the weight of their guns, just to mount an experimental black box that most RAF officers thought was pure fantasy. The display was a 5-in cathode ray tube that glowed ghostly green in the darkness. 2 traces appeared on the screen, one showing targets to the left or right, another showing targets above or below. When the blips merged in the center, you were theoretically pointing straight at the target. The maximum detection range was 3 mm under ideal conditions, less than 90 seconds of closing time at typical engagement speeds. The minimum range was about 400 FT, which meant the radar picture vanished just before you needed to see the target to shoot it. This blind zone terrified pilots. You'd be diving toward a bomber you couldn't see, watching it disappear from your screen and praying you'd spot it before you collided. The first test installation went into a Bristol Benham in August 1939, days before Germany invaded Poland. Flight Lieutenant George Stainforth took it up for trials. The equipment worked barely. The radar could detect other aircraft, but the set was temperamental. The display was nearly impossible to interpret while flying, and the transmitter generated so much heat that it scorched the aircraft's internal structure. After one flight, maintenance crews found the metal framework around the transmitter had warped from thermal stress. Nobody in Fighter Command wanted it. Squadron commanders looked at the weight penalty, the complexity, the failure rate, and the marginal performance, and they made perfectly rational decisions. Take this rubbish out of my aircraft was the polite version. Some were less diplomatic. The AI mate and the required a 2-man crew, a pilot and a radar operator. Single-seat fighters couldn't use it. That meant twin-engine aircraft, Ben Blems which were slow and unmaneuverable, or bow fighters which hadn't even entered service yet. You were asking veteran pilots to abandon their nimble Hurricanes for sluggish night bombers that had been converted into makeshift fighters and filled with experimental electronics. The operational debut was a disaster. In December 1940, No. 25 Squadron received the first AI-equipped bow fighters. The first operational sortie ended when the radar caught fire. The second sortie, radar malfunction. Third sortie, the operator couldn't interpret the display. Fourth sortie, successful detection at 2 miles, but that target escaped before the pilot achieved visual contact. The squadron flew 47 AI-equipped sorties in December and January and scored 0 confirmed kills. Worse, the equipment actively endangered crews. The transmitter generated powerful radio frequency energy in a confined space. Operators reported headaches, nausea, and dizziness after long sorties. Early symptoms of what we now know as RF exposure. The display's glow ruined the pilot's natural night vision, making visual acquisition even harder. And the sheer complexity meant that most sets were unserviceable at any given time. Maintenance crews trained on conventional aircraft systems struggled with the temperamental electronics. Vacuum tubes failed, connections corroded, calibration drifted. On a good day, half the squadron's AI sets would be operational. On a bad day, none. Yet Bowen and his team kept pushing. They knew the concept was sound. They just needed time to make it work. The complaints weren't unreasonable. Flight Lieutenant Charles Widdows, an experienced night fighter pilot with No. 604 Squadron, put it bluntly in his after-action report from February 1941. The AI set added 600 lb to an already overweight aircraft, reduced our maximum speed by 15 mph, failed to function on 4 out of 7 sorties, and on the 3 occasions it worked. We never closed to visual range before losing contact. He concluded with a recommendation that the equipment be removed and replaced with additional fuel tanks. His commanding officer endorsed the recommendation. The 3-mile maximum range wasn't theoretical speculation. It was an optimistic estimate. In practice, detection ranges varied wildly depending on altitude, weather, the target's aspect angle, and whether Mercury was in retrograde. On humid nights, water vapor absorbed the radar signal. At high altitude, where the air was thinner and drier, range improved slightly. But if the target bomber was flying away from you, presenting its tail, a much smaller radar cross-section than its broad wings, detection range could drop to barely a mile. That gave you perhaps 30 seconds to close, confirm the target was hostile, maneuver into firing position, and engage before overshooting. The minimum range problem was arguably worse. Below 400 FT, the AI Magnetron display went blank. The transmitted pulse and the returning echo overlapped, creating a dead zone. Standard intercept procedure required the radar operator to guide the pilot to within 1,000 ft, then call contact lost visual search. The pilot would then peer into the darkness, hoping to spot exhaust flames or a silhouette. On moonless nights, this rarely worked. Pilots reported the horrifying experience of knowing a bomber was directly ahead, invisible, while they hurtled toward it at a combined closing speed of 400 mph. Several near collisions convinced some crews that the equipment was more dangerous than useful. Heat remained a constant problem. The AI Men 3's transmitter operated at high power in an enclosed space. Cockpit temperatures could reach 110 degrees, even at altitude, where outside temperatures hovered around -20. Operators sat in their heavy flight suits, sweating, trying to interpret a flickering green display while suffering from heat exhaustion. Some crews resorted to wearing minimal clothing under their suits, which created new problems when they needed to bail out over the channel in winter. Reliability was abysmal. An internal RAF survey from March 1941 found that AI-equipped aircraft had a serviceability rate of 38%, meaning that on any given day, fewer than 4 out of 10 aircraft had functioning radar. The vacuum tubes were fragile and burned out frequently. The antenna arrays mounted on the aircraft's nose and wings were damaged by weather, vibration, and ground crew errors. Moisture infiltrated the electronics. The power supplies, crude by modern standards, delivered inconsistent voltage that caused components to drift out of calibration or fail completely. Training was inadequate. Radar operators received perhaps 20 hours of instruction before being declared operational. Most had never seen an oscilloscope before joining the RAF. They were expected to interpret complex signals, Distinguish real targets from ground clutter and weather returns, calculate intercept angles mentally, and provide precise verbal guidance to their pilots, all while being shaken around in a combat aircraft at night. The learning curve was steep, and the consequences of mistakes were measured in wasted sorties and dead civilians on the ground. Pilots hated losing speed and maneuverability. The Beaufighter was already heavier and less agile than the bombers it hunted. Adding 600 lb of radar equipment made it worse. In the unlikely event a German night fighter appeared, AI-equipped Beaufighters were sitting ducks. Some pilots privately admitted they'd jettison the radar equipment if they could, accepting the weight penalty only because orders required it. By April 1941, the useless label seemed entirely justified. The equipment was unreliable, dangerous, difficult to operate, and had produced minimal results. Several squadron commanders formally requested permission to remove the AI sets. Some crews began developing alternative tactics that didn't rely on the cursed green boxes. John Cunningham shot down his first Luftwaffe bomber on the night of November 19, 1940. By May 1941, he destroyed 15 enemy aircraft, making him the RAF's most successful night fighter pilot. The press wanted to know his secret. The Air Ministry's answer was brilliant misdirection carrots. The official story went like this. Cunningham had exceptional night vision, cultivated through a special diet rich in vitamin A. He ate carrots constantly, raw carrots, cooked carrots, carrot juice. The vitamin improved his eyesight to superhuman levels, allowing him to spot German bombers in conditions where other pilots saw nothing. The Ministry of Information pushed this narrative hard. Newspapers ran features about Cat's Eyes Cunningham and his legendary vision. The government launched public campaigns encouraging citizens to eat carrots to improve their own night vision during blackouts. Posters appeared. Carrots keep you healthy and help you see in the blackout. It was complete fabrication. Well, partial fabrication. Vitamin A does support healthy vision, and deficiency can cause night blindness. But no amount of carrots will give you superhuman abilities. Cunningham's success had nothing to do with his diet and everything to do with the AI Maxiphoradar set in his Beaufighter and the exceptional skill of his radar operator, Flying Officer Jimmy Ronsley. The deception operation served multiple purposes. First, it explained away Cunningham's success without revealing Britain's radar capabilities. German intelligence was desperately trying to understand why RAF night fighter effectiveness had suddenly improved. If they concluded it was simply better pilot selection and training enhanced by nutrition, they might not investigate technological explanations. Second, the carrot campaign had genuine public health benefits during wartime rationing, encouraging consumption of a vitamin-rich vegetable that Britain could grow domestically. Third, it protected the men whose lives depended on AI radar remaining secret, because by mid-1941 the technology was finally working, not consistently, not reliably, but often enough that trained crews were scoring kills. The difference wasn't the equipment. It was still the same temperamental AI MLV-4 that Squadron Chad cursed 6 months earlier. The difference was experience. Operators like Ronsley had flown hundreds of sorties. They'd learned to distinguish real targets from phantom returns. They developed techniques for tracking targets through the radar's limitations. They'd built an instinctive understanding of intercept geometry that let them guide their pilots with precision. Ronsley's running commentary during intercepts became legendary. Contact 2M slightly left. Turn port 5 to green steady. Range closing 112M. Target steady on course. Increase speed 1 mile. Now still slightly left. Come port 2-3/4 of a mile. Target climbing slightly. Increase your climb rate. 1/2 mile dead ahead. You should be getting visual any moment. And Cunningham would peer ahead, and there, a faint shadow against clouds. Exhaust flames flickering. The bomber would materialize not through superhuman vision, but because Ronsley had positioned him perfectly. Other crews began achieving similar success. Flight Lieutenant Mike Constable Maxwell and his operator, Sergeant Gregory, shot down 3 bombers in one night on May 10, 1941. Wing Commander Basil Embry scored 4 kills in April using AI Mach-4. Number 604 Squadron, the same unit that had recommended removing the equipment 4 months earlier, destroyed 11 German aircraft in May alone. The kill rate was climbing. Not dramatically, not enough to stop the Blitz, but enough to prove the concept worked. The Germans never figured it out. Luftwaffe intelligence reports from 1941 attributed RAF night fighter success to improved searchlight coordination, better pilot selection, and yes, enhanced nutrition programs. A captured German document from July 1941 specifically mentioned British propaganda about carrots improving night vision, and concluded it was probably exaggerated, but might indicate some advancement in pilot training methods. They were looking in entirely the wrong direction. Cunningham himself played along. When reporters asked about his secret, he'd smile and mention his fondness for carrots. He described techniques for preserving night vision, avoiding bright lights, allowing 30 minutes for eye adaptation. He'd credit his ground controllers and his own experience. He never ever mentioned the green glowing display in his cockpit or the man sitting behind him calling out ranges and bearings. The secret held, and while it held, crews learned their craft and the technology slowly, painfully improved. February 1940, Birmingham University. John Randall and Harry Boot were working with a device that would change everything, the cavity magnetron. This wasn't incremental improvement. This was a technological leap that made previous radar systems look like clockwork toys. The cavity magnetron could generate microwave frequencies at power levels previously thought impossible. Where the AI-Man 3 operated at 1.5 meter wavelength, the new magnetron worked at 10 cm. Physics made this revolutionary. Shorter wavelengths meant sharper resolution. A 10 cm radar beam could distinguish objects just feet apart, where the old 1.5 meter sets could barely separate targets hundreds of yards distant. The magnetron was also smaller, lighter, and more efficient. A complete radar set using cavity magnetron technology could weigh half as much as the AI Mach while delivering 4 times the performance. Detection ranges jumped to 6 miles. Minimum range dropped to under 300 km and the dead zone shrank, but Britain couldn't exploit it alone. Manufacturing cavity magnetrons at scale required industrial capacity that British factories under constant bombing simply didn't have. In September 1940, the TISED mission, named after physicist Henry Tizard, carried Britain's most precious military secrets to America. In a black metal box, they transported a cavity magnetron to the United States. It was arguably the most valuable cargo ever shipped across the Atlantic. American engineers at the Radiation Laboratory at MIT saw the magnetron and recognized its potential immediately. By March 1941, they designed production methods. By October 1941, factories were manufacturing them in quantity. American industrial capacity, not yet constrained by war, ramped up production faster than anyone thought possible. Cavity magnetrons began flowing back to Britain in early 1942. The AI Mach 7 entered service in May 1942. It used the new centimetric wavelength and provided radar operators with a display that actually made sense. Instead of abstract traces on a cathode ray tube, the MEK-7 showed a planned position indicator, essentially a radar map. Targets appeared as bright blips on a dark screen with range rings marking distance. An operator could see everything within 6 miles simultaneously. The target's position, its movement, even other aircraft in the area. The presentation was intuitive enough that pilots could interpret it themselves if needed. But the MK-7 was just the beginning. The AI Mach Fate, which entered squadron service in early 1943, combined American manufacturing with British operational experience. Detection range reached 8 miles against bomberized targets. Minimum range dropped to 400 ft. Still a blind zone, but manageable. The equipment was more reliable, easier to maintain, and actually lighter than what it replaced. A complete AI MEK-8 installation weighed 450 lb, 150 lb less than the old Mk-3. The Mosquito Night Fighter made everything better. This aircraft was fast, 370 mph at altitude, faster than most bombers it hunted. It was maneuverable. It had range, and it was specifically designed to accommodate radar equipment. The AI Mach fit perfectly in the Mosquito's nose with antennas integrated into the airframe, rather than bolted on as afterthoughts. The pilot and radar operator sat side by side, improving communication. When a Mosquito crew achieved radar contact, they had speed to close quickly and agility to maneuver for the kill. The Americans contributed another innovation, the SCR-720, their version of British AI radar with additional features. Some RAF squadrons adopted it in late 1943. The SCR-720 offered 10-mile detection range and included a beacon mode that helped fighters find their way home in bad weather, a feature that saved numerous crews who would otherwise have been lost over the North Sea. Training improved dramatically. By 1943, Radar operators received 200 hours of instruction before operational deployment. They practiced on ground simulators that replicated airborne intercepts. They flew dozens of training sorties with experienced crews. The RAF established specialized night fighter training units where new pilots and operators learned intercept techniques in a controlled environment before facing live combat. Maintenance procedures evolved. Ground crews now understood the equipment. They had proper test equipment, detailed manuals, and adequate spare parts. Serviceability rates climbed above 80%. On any given night in late 1943, 8 out of 10 AI-equipped fighters had functioning radar. A complete reversal from 2 years earlier. The technology had matured, the tactics had matured, the crews had matured. By the end of 1943, the useless equipment had become the most lethal night fighting system in the world. The numbers tell the story. Between January 1941 and May 1944, RF night fighters equipped with AI radar destroyed over 600 Luftwaffe bombers during night operations over Britain and occupied Europe. This figure represents confirmed kills. Aircraft witnessed crashing or exploding with wreckage located and verified. The actual number was almost certainly higher, as many damaged bombers limped back across the channel only to crash in France or simply disappear into the North Sea. Number 85 Squadron led the tally with 108 confirmed victories. They'd been among the first units to receive AI-equipped bow fighters in early 1941, suffering through the equipment's teething problems while developing tactics that other squadrons would later adopt. By 1943, flying Mosquitoes with AI Macav-8 radar, they were destroying bombers at a rate that would have seemed impossible 2 years earlier. Their top crew, Squadron Leader Michael Allen and Flight Lieutenant Tom Slack, accounted for 21 of those kills personally. Non-29 Squadron claimed 104 victories. They specialized in long-range intruder missions using AI radar to hunt German bombers over France and the Low Countries as they formed a pour, returned to base. This was extraordinarily dangerous work, flying deep into enemy territory, often alone, relying entirely on radar to find targets, while German ground controllers vetoed their own night fighters toward the intruders. Flight Lieutenant Richard Stevens and his operator, Flying Officer Kellett, scored 14 confirmed kills on these missions before Stevens was shot down over Belgium in October 1943. No, 604 Squadron. Remember, this was the unit that wanted to remove AI equipment in early 1941. Destroyed 98 German aircraft. John Cunningham, the Cat's Eyes pilot, scored most of his 20 confirmed victories while flying with 604. His success convinced other skeptical crews that the technology was worth mastering. By mid-1942, 600th Squadron had become one of the most effective night fighter units in fighter command. The kill rate accelerated dramatically after mid-1942. In all of 1941, AI-equipped night fighters destroyed approximately 85 German aircraft. In 1942, that number jumped to 175. In 1943, it reached 230. The first 4 months of 1944 alone saw 110 confirmed kills. The improvement reflected better equipment, better training, and better tactics, but also reflected the fact that the Luftwaffe was now flying more missions over Britain again after a relative lull in late 1941 and early 1942. Operation Steinbach. The Germans called it the Baby Blitz, ran from January to May 1944. Hitler, enraged by RAF bombing of German cities, ordered renewed attacks on London. The Luftwaffe scraped together roughly 500 bombers and began night raids. They flew straight into a killing zone. RF night fighters, now equipped with mature AI radar and flown by experienced crews, massacred them. On the night of February 20, 1944, German bombers flew 127 sorties against London. RF night fighters destroyed 25 of them, a loss rate of nearly 20%. No air force can sustain such casualties. The tactics had evolved considerably. Ground controllers now worked in close coordination with airborne radar. A typical interception in 1944 looked like this. Ground radar detected an incoming raid and vetoed a Mosquito to within 10 miles. The Mosquito's AI radar picked up contacts. Multiple bombers scattered across the formation. The radar operator selected a target and guided his pilot into position. At 2 miles, the pilot could often see exhaust flames. At 1 mile, the bomber's silhouette was visible. The Mosquito close to 300 FT below the radar's minimum range, but close enough for certain visual identification. 4 20-ply cannons opened fire. The bomber exploded or went down trailing flame. The Mosquito immediately turned toward the next contact already visible on the radar display. On exceptional nights, single crews destroyed 3 or 4 bombers in one sort. The psychological impact on German crews was devastating. They'd grown accustomed to British night fighters being rare, ineffective nuisances. Suddenly, in late 1942 and 1943, bombers were exploding without warning. No searchlights, no warning, just sudden catastrophic cannon fire from the darkness. German bomber crews began refusing missions. Morale collapsed. Units reported aircraft lost to unknown causes that were almost certainly shot down by AI-equipped fighters, but never witnessed. By May 1944, the Luftwaffe had effectively conceded the night sky over Britain. Operation Steinbach ended with German bomber losses exceeding 50% of committed aircraft when you counted both combat losses and operational accidents, caused by crews rushing takeoffs and landings to minimize exposure time. The useless radar had achieved what had seemed impossible in 1940. It had made the night as dangerous for bombers as daylight. The strategic consequences rippled far beyond the immediate kill numbers. In 1940 and early 1941, German bombers had operated with near impunity after dark, forcing Britain to shut down war production in targeted cities every time air raid sirens wailed. Workers fled to shelters. Assembly lines stopped. Dock workers abandoned cargo ships. The economic cost was immense, not just from physical destruction, but from lost productivity. A single raid could halt manufacturing in an entire industrial region for 8 to 12 hours. By 1943, that calculus had reversed. Luftwaffe commanders knew that sending bombers over Britain meant accepting losses they couldn't replace. Germany was now fighting on multiple fronts. The Eastern Front consumed men and material at horrific rates. The Mediterranean theater demanded resources, and the Wehrmacht was preparing for the inevitable Allied invasion of France. The Luftwaffe couldn't afford to waste experienced bomber crews on missions that had minimal impact and maximum casualties. RAF night fighters equipped with AI radar had effectively removed Germany's ability to conduct strategic bombing of Britain. This freed British industrial capacity completely. Factories ran night shifts without interruption. Ports operated 24 hours daily. The infrastructure that would supply the D-Day invasion, the largest amphibious operation in history, was built and assembled without German interference. Think about that. Millions of tons of supplies, thousands of vehicles, entire prefabricated harbors accumulated in southern England, while the Luftwaffe watched helplessly from across the channel. They knew the invasion was coming. They could see the buildup from reconnaissance flights, but they couldn't stop it, couldn't even significantly disrupt it, because their bombers couldn't survive British night fighters. The technology pioneered in air radar became the foundation for modern fighter intercept doctrine. Every air force in the world now trains fighter pilots to use radar as their primary sensor, with visual identification as confirmation rather than the primary detection method. The concept of the two-man crew, pilot and weapon systems officer, originated with AI radar operators and remains standard in advanced fighters. The ground-controlled intercept procedures developed during the Battle of Britain evolved into modern air traffic control and military command and control systems. The cavity magnetron that made advanced AI radar possible went on to enable dozens of other technologies. The same physics that let British fighters detect bombers at 8 miles also enabled naval surface search radar that could spot submarine periscopes, fire control radar for anti-aircraft guns, and eventually, after the war, the microwave oven that sits in your kitchen. That device cooking your leftovers is a direct descendant of the technology that saved Britain. There's a darker legacy, too. The arms race in radar and counter-radar measures that began with AI radar has never stopped. Modern stealth aircraft are designed specifically to defeat radar detection. Electronic warfare, jamming, deception, signal intelligence is now a critical component of every military conflict. The cat-and-mouse game between detection and evasion that started over Britain in 1940 continues in every contested airspace worldwide. Syria, Ukraine, the South China Sea all feature the same fundamental struggle, one side trying to see, the other trying to remain invisible. But in 1944, standing in the operations room at RAF Hunden, watching tote boards show German bombers being destroyed faster than they could be launched, Air Chief Marshal Roderick Hill could see the transformation clearly. The same Luftwaffe that had burned Coventry, devastated London, and killed tens of thousands of civilians was now broken as an offensive force. Not destroyed, they'd fight on for another year, but broken as a threat to British cities and industry. Those 600 confirmed kills represented more than statistics. Each was a bomber crew that wouldn't strike again, a load of explosives that wouldn't fall on civilian homes, a night when workers could sleep and factories could run. The useless AI radar that squadron commanders had wanted to throw out in 1941 had become the weapon that won the night battle. It hadn't been easy. It hadn't been quick. Crews had died learning to use equipment that failed constantly. Engineers had worked 18-hour days improving systems that seemed fundamentally flawed. Radar operators had flown hundreds of sorties, straining their eyes at flickering green displays while their aircraft bounced through flak and weather. But they'd persevered. They'd turned a 600 lb liability into a war-winning capability. They'd proven that persistence and incremental improvement could overcome apparently insurmountable technical obstacles. And they'd ensured that when dawn broke on May 9, 1945, and the war in Europe finally ended, Britain still stood battered, exhausted, but undefeated. The night fighters had held the line.